Our guest speaker today, as you well know, is Randall Carlson. He'll be speaking on Earth changes and the precession of the Equinox. Randall is a local architectural designer and master builder, Freemason, teacher, geometrician, geomythologist, and geological worker, explorer. Randall has more than 35 years of exploration and research into the interface between ancient mysteries and modern science. Randall will try to dispel much of the misunderstandings surrounding the subject of Earth changes and to place the subject on a solid scientific foundation. To this end, he will seek to synthesize the great mystic traditions or mythic traditions of the past with cutting-edge scientific research in the fields of geology, astronomy, paleontology, archaeology, and ancient history. Please welcome Randall Carlson.
Some of you who've been attending my talks kind of know some of the things that I address. I've been trying to educate people a lot about the concept of the Great Year because that's a framework for understanding all kinds of things that are going on right now. There's a lot of interest in the Mayan calendar and the 2012 date and what that means. And I try to explain to people that if you want to understand what the significance of to that date is, and there's a lot of fuzzy thinking about it, a lot of extravagant claims, overblown claims, a lot of fears about catastrophic destruction, apocalyptic type events, that sort of a thing associated with the year 2012. Other people think it's going to launch us into sort of the New Age equivalent of the rapture, and we're all going to become enlightened by 2013. I look at it more from the standpoint of an astronomer. Not that I'm an astronomer, but I have been an amateur astronomer and studied astronomy for many, many years. So one of the tenets that I proclaim is that if you want to make sense out of the significance of that date, you have to understand the whole concept of the Great Year as we have inherited it from the ancient world. And the concept or model of the Great Year was very universal throughout the ancient world. And essentially what it is a larger cycle. It's the next largest cycle, cosmic cycle, if you will, outside of our immediate experience, our framework of experience. And one of the most important concepts in arcane traditions that I have come to appreciate, primarily because of my studies of sacred geometry and geology, in both of those areas, there's a concept called scale invariance that's very powerful for allowing one to understand patterns that might normally be outside the human purview or outside the human scale of reference. And that goes both to the micro scale as well as to the macro scale. In geology, you'll see, and I'm going to be showing you some geological photographs here in a few minutes, always you will see that in the photograph there will be typically the geologists, what they will frequently do is they'll put, if it's a smaller scale feature that they're looking at, they'll put a rock pick in the picture. If it's a larger picture, they'll have a person standing in the picture. The reason for that is that oftentimes if you take any reference out of there that allows you to see what the scale is, you can't really tell, the scale of what you're looking at. And so by putting an object, a recognizable object or a human figure in there, you can get a sense of the scale. Well, this is because many geological features are scale invariant. In the study of sacred geometry, we encounter the same concept because we find out that there are patterns that replicate themselves through multiple scales of phenomena. And that can go all the way from the atomic and subatomic levels to the human level, all the way to the macrocosmic level. And in sacred geometry classes, that's one of the things I like to address, is to try to teach this concept of scale invariance and how it allows us to understand relationships that are typically outside of our frame of reference or frame of experience or our frame of perception. So when we talk about the Great Year, the same principle holds in the measurement of time as well as space. When I talk about a geological phenomena and say that we have to put a human in the picture so you can understand what the scale of what you're looking at. In temporal phenomena, or phenomena having to do with time, we find that the same concept holds as well. And ancient peoples seem to have understood this idea that there were these multiple or multivariate scales of reference. By understanding the patterns and proportions of a reference frame that is closer to us on the human scale, we can then understand something that would be ordinarily outside of our frame of reference. So when we look, for example, at time measurement, we have the obvious ones that we all go by a calendar, we all go by a clock. There's a clock up on the wall up there, and if you look at that clock back there, you'll see that there are 12 numbers. You've got a circle. It's divided into 12 equal divisions. Well, that clock that's hanging on the wall is also an exact model for the great year. The precessional cycle with the 12 ages of the zodiac in it, during which each one being reckoned by the time that the vernal equinox transits through that sign of the zodiac. So you have a wheel that represents a roughly 26,000 year cycle. It's divided into 12 equal divisions. Each of those equal divisions is named for a constellation of stars that is found within that 30-degree slice of the total circle. And of course, there are all the familiar signs of the zodiac, starting with Aries, and then moving around and finishing with Capricorn. Well, okay, so the idea is that during the course of a year, we will see, because of the Earth's movement around the sun gives the illusion of transiting or passing through the 12 signs in turn. Also, through the course of the year, there are 4 stations, four points within that circle, within that wheel, that were significant to the ancient people. And those can be likened to 4 stations that are also significant to the cycle of one day, which we refer to in astronomy as a diurnal cycle, which is essentially the turning of one turn of the Earth on its axis, so that a position on the surface of the Earth is in the same exact relative position to the sun. That's the 24-hour cycle. That's what we're measuring with the clock. Now, you know that in the course of the day, there are 4 stations, 4 hinge points, if you will, that we kind of anchor the wheel to. And that would, of course, be midnight, which is not only the exact moment of midnight is not only the end of the day before, it's the beginning of the following day. Then that following day is divided into 4 stations. And we could symbolize those 4 stations within the clock wheel by midnight, dawn, high noon, and dusk. And they would roughly coincide with midnight, 6 a.m., high noon, and 6 p.m. And of course, in the real world, they're only occasionally and only at certain positions on the surface of the Earth are those 4 periods going to be equal. Once we start moving around through the course of the year, start moving around on the surface of the Earth, of course, those 4 quadrants of that diurnal cycle are no longer equal length. But nonetheless, it gives us a convenient framework for referring and for understanding and having a sense. Try to imagine, if you will, a little mental exercise if we just took all clocks and watches and timekeeping pieces suddenly disappeared. It would be disorienting, wouldn't it? It would require some reorienting to our day-to-day life if we didn't have clocks. Okay, now imagine a calendar. We have a calendar marks the annual cycle of the Earth around the sun. And in the old days, the belief was that once upon a time there was an idealized year that consisted of 360 days. It's been speculated that the Sumerians, in coming up with what's known as the sexagesimal division of all circles into 360 degrees, was based upon their belief that there was once an idealized or sacred year whose actual length was exactly 360 days. And we know, of course, that it's not. And if we had a 360-day calendar, it wouldn't take very long before that calendar to be completely out of sync with the real world. Okay, so we know that in the real world, it's 365 and roughly 1/4 days for the Earth to make that transit around the sun. But within that cycle, we think in order for us to have a frame of reference that we can comprehend we have what we could call a fiducial point. If you're an astrologer, you know what that means. It means that you've got some point at which you can reckon everything, from which you can measure everything. If you're doing a race around a racetrack, you've got to have a definite starting point and a definite ending point. If you don't, who's won the race, right? Well, in a calendar, you've got a starting point, which, you know, midnight of January 1st, at that one moment, simultaneously, one year ends, another year begins. Then in the course of that cycle, that year, we have 4 quadrants, just like we do in the cycle of the day. Those 4 quadrants would be the 4 seasons, you know, and those 4 seasons are measured by the motion of the vernal equinox. And what is the vernal equinox? What is it? Well, yes, we know it's spring, but that's a name for it. It's the name of the season, but what is happening on the vernal equinox? Yes, the sun is at a certain point. We're getting from the general down to the more specific. What is the certain point? Thank you, Brian. Good man. What he just said was there are 2 great planes, and I guess what I should do is to pull up an image here so that as I'm talking, you will be able to see this image for yourself. And at that point, we will turn the lights down. I think we've got some more people coming in, so let's just hold off for a second on the lights. Okay. Okay, so what Brian said while this is booting up is that there are 4 quadrants, or rather there are 2 great planes that you need to learn about. One of them is called the plane of the ecliptic, and one is called the celestial equator. Who can tell me what the plane of the ecliptic is? Okay, the plane of the ecliptic, I'm going to find a good graphic here to show you what the plane is. But very simply, now I want you to remember this, because when I come back, whenever that's going to be, there's going to be a test, and I'm going to see who remembers this. The plane of the ecliptic is the orbital plane of the planets around the sun. And it's a band that's 16 degrees wide, because it's within that, it's sometimes called the belt of the ecliptic. It's 16 degrees wide, because within that 16 degrees is where we find the 12 signs of the zodiac. And we can narrow it down and say precisely that the plane of the ecliptic is the plane that is swept out by the Earth moving around the sun. And that would be 0 degrees north or south celestial latitude. Sun, Earth is a point in space going around the sun, sweeps out this plane. All of the planets within the solar system move in that same relative plane. Not exactly. All the planets are slightly tilted a little bit, so that when you've included the greatest tilt, the actual band measured with respect to Earth's orbital plane is 8 degrees above Earth's orbital plane and 8 degrees below. Now, let me see here if I can find this graphic I wanted to show you. Well, if you'd stay back there by the lights, I mean, how does it work when you're on here? Because actually this will show up brighter in the camera with the lights down, I think. That's been my experience. Want to try it? All right, now this graphic, what's happening? Is it going to work, Brian? All right, let's take a look at this graphic, because this graphic will kind of display the idea. We have a green circle, and we're a little bit fuzzy here. Okay, the yellow circle, we can think of it being yellow because the sun is yellow. Okay, and we have the sun showing here, 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 and here, and we have the Earth in the center. This is a geocentric model, which of course is not astronomically accurate, but it does provide a convenient way for understanding these relationships. Again, the Earth is going around the sun and not the sun around the Earth. However, as the Earth goes around the sun, you can think about this. If you're looking at me, okay, and you look at what's behind me, and you're watching me as I walk in a circle around you, obviously what's behind me, the backdrop, is going to be constantly changing. And it's not you that's moving, it's me that's moving. Well, in this case, it's the Earth around the sun. So the converse of that is, as I'm moving around the room, now the TV's behind me. If I walk over there, the bookcase is behind me. If I walk over there, Brian's behind me. The converse of that is if I'm looking at you, if Brian is behind me and I'm looking at you, then the screen is behind you. Well, in the case of the Earth and the Sun, we're going around the Sun. The Sun appears to be traveling through the 12 signs of the zodiac. And here's the wheel. You see, here's the wheel, starting right here with 1, going on around. You can probably see there's Leo, there's Virgo, and there's Aries, there's Pisces, and here's Sagittarius right here. Now, what you need to look at is this cross, because that's the 4 stations I was talking about. In the diurnal cycle, we have midnight, 6 a.m., high noon, 6 p.m. Okay, midnight, dawn, noon, and dusk, corresponding. In the course of the year, we have 4 stations represented by spring, summer, winter, and fall. When the sun, now if you look at this, you'll see there's the yellow band, and then there's the green band. Those are the 2 planes. The plane of the ecliptic would be the yellow band. The green one is the celestial equator. I didn't bring my globe model, but if you look at any globe, you'll see that it's tilted 23.5 degrees. Its axis is not vertical up and down. You've probably all seen that, right? Globes are tilted 23.5 degrees. That's this angle right here, 23.5 degrees of tilt. Well, the Earth's axis is tilted, but it's not fixed in its orientation in space. It's moving around, sweeping out almost an hourglass shape, and as it's moving like this, Earth's equator is rocking or oscillating around with it. We call it the Earth's equator. Now we project that equator out into space, and Earth's equator projected into space becomes the celestial equator. Now, Earth is rocking around, doing this motion like this. Its equator is going up and down as the Earth spins around.
Can you point that out on there because they can't see you?
I'm about to do that. When you take the Earth around like that, what that means is this green line coincides to Earth's equator. So it's moving. It's moving like this. And as that moves, the intersection of those 2 planes, defined by that line right there, is rotating. In fact, the whole cross that you see is rotating. This is the equinoctial line, that's the solstitial line. So winter solstice here, summer solstice there, vernal equinox here, fall equinox there. And that whole cross is rotating. The entire period takes roughly 26,000 years. Astronomers don't know exactly because the motion of these intersection points has been measured. And it comes out to be just slightly more than 50 seconds of arc per year. What does that mean? Think of it this way, 50 seconds of arc per year, every circle divides into 360 degrees, each degree divides into 60 minutes, just like on the clock. Every hour divides into 60 minutes. Every minute divides into 60 seconds. In geometry, every circle has 360 degrees. Every degree divides into 60 minutes of arc. And every one of those minutes of arc divides into seconds of arc. So you can see that if you're looking at a circle with 360 degree equally spaced increments around it, they're going to be pretty small. Now, if you divide each one of those into 60 parts, they're going to be really small. They're going to be, in fact, really minute. That's why we call them minutes, because they're minute. If you take each one of those minutes and further subdivide it into a second order of minuteness, we get a second of arc, which is very small. In fact, you can detect a second of arc of motion in the sky. Now, if you're looking out there in the sky, what is a relative dimension that we could understand what seconds or minutes or degrees would actually mean when looking at the sky? Well, if you go out and you look at the orb of the full moon, which you probably know from pictures of eclipses, and since you're not blind, you probably haven't been looking directly at eclipses, but if you've seen pictures of a perfect eclipse, you're going to know that the orb of the moon precisely superimposes on top of the disk of the sun, right? They both have the same angular dimension relative to our perspective, and it's 1/2 a degree. 1/2 of 1 degree. That means 30 minutes of arc. 30 minutes of arc. Okay, now think about this. If I say 1/2 a degree, and you know that there are 360 degrees in a circle, we can think of it this way. If we took the moon and created a string of beads out of lunar orbs, 720 of them would make the complete circle in the orbit of the moon. Does that make sense? Because each one is 1/2 a degree, and there's 360 degrees, so every degree there'd be 2 orbs of the moon. 720 of them would make a complete loop around. Now, if you think of the moon as 30 minutes of arc, take 1/30th of that distance, and you've got 60 seconds of arc. 1/30th of that distance across the face of the full moon. The motion of the precession of the equinoxes, the vernal equinox, this, in fact the solstice as well, because they're all moving at the same rate, is 50 seconds of arc. So almost, but not quite, 1/30th of the distance across the full moon. Now what does that translate into? In terms of human perspective, what that translates into is that vernal equinox, those lines have rotated 1 degree in every 72 years. In fact, you could think of the correlation between 1 degree of motion of the vernal equinox roughly corresponding to an average human lifespan. And now we get to that's another interesting example of scale invariance, because following that model, we could very, very logically divide a human lifespan into 4 ages or 4 epochs or 4 seasons. That if we took the average lifespan of 72 years, then we've got 18 years from birth to presumably adults. At least in the old days when you were 18, you were an adult. Maybe these days you still need another 10 years to emotionally and psychologically mature is what it seems like. But that's another subject altogether. And we're not going to talk about public education here today. So anyways, go from 18 to 36, from 36 to 54, from 54 to 72, and now you have a cycle of a life that could be thought of in terms of 4. Just like the Greeks, you had the Golden Age, the Silver Age, the Bronze Age, and the Iron Age. Think of your own life. Think of the golden years, right, of your youth, right? Okay. So in a way, there's a scale invariance, which is interesting. Now, if you take that 72 years and you express it in terms of days, and I'll go back to the idea of the sacred calendar that I mentioned earlier. The sacred calendar, like of the Sumerians and others, I mean, this was very universal over the ancient world that they ran 2 calendars, a sacred calendar and a secular calendar. Secular calendar being the actual calendar that marks the course of the year, 365 days. The sacred calendar being a calendar of 360 days, because in their minds, in their concepts, that 360-day cycle represented an idealized design, an idealized pattern, or an idealized machine for synchronization of all the great cosmic cycles. But if we go 360-day year, what you'll discover is that 72 years of 360 days is exactly 25,920 days. Well, 25,920 years was the traditional belief in the length of the precessional cycle. I said earlier that astronomy measures it at approximately 26,000 years. It's not known with precision because of the fact that we can say that motion is a little bit more than 50 seconds of arc per year, as I said. However, we've only measured it using modern astronomical instrumentation over a period of a few centuries. If we were able to measure it through the full cycle, we would probably discover that rate is not perfectly constant. It probably deviates back and forth, sometimes a little faster, sometimes a little slower than that idealized 50 seconds of arc per year. If it was 50 seconds of arc per year exact, then it would be the traditional sacred number of 25,920 years for this complete cycle of the great year to take place. So here's a beautiful example of this scale invariant phenomena. If you think of a life, 25,920 days, every day of your life then corresponds by analogy and by scale to 1 year, 1 trip of the Earth around the sun relative to this greater cycle. So you can put it in that framework to try to get a handle on it. A human life divided into 25,920 parts gives you almost exactly 1 day. That day to a human life is the same as our annual year trip around the sun is to the great year. And that's pretty phenomenal when you begin to contemplate that and think about that kind of patterns and harmonies that transcend the scales of experience. And we can, again, like I was saying, we can go to the micro scale or we can go to the macro scale. My suspicion is, and in fact I've seen very tantalizing hints within the various traditions, that beyond the great year, there's yet another cycle. Now, astronomers will recognize that yes, beyond this precessional cycle, there is a galactic cycle. But when you begin to look at the scales, what you realize is that, and I'm not going to get into this in extraordinary detail today. I'm just trying to give you the general outlines of the idea. If you think about satellite going around the Earth, satellite in our case would be the moon, right? And again, in an idealized calendar, 12 months of 30 days would give us that 360 year sacred year, right? Well, we go from satellites around planets, planets around suns or stars, stars around the center of the galaxies. Now, we know that's going on, and we know it's probably going to take on the order of 250 million years for that process to take place. But if we go by scale, from satellite to planet, from planet to star, star to galaxy, what we discover is there's a gap between star and galaxy. Now, like I said, there are some interesting tantalizing hints from ancient traditions that some groups, Egyptians for example, believed in a Sothic cycle. Cycles sometimes related to certain other stars that basically postulated this, that between the moon going around the Earth going around the sun going around the center of the galaxy, that the sun was actually going around some sub-galactic center, which in its turn was then wheeling around the galaxy. And if you postulate such a thing, you actually then fill that gap of scales that's there now when you go from sun to galaxy. I don't know if any of you have studied the, I would bet that it's somewhere within the Theosophical teaching you could find some reference to that. I know it's in the Gurdjieffian teaching and Uspensky and Rodney Collin and a lot of these other people, a lot of the Western occultists and stuff that wrote around the turn of the century were making references and remarks to the possibility of there being a subgalactic orbital center. And if you look at a lot of the near stars that are, say, within 10 to 20 light years of Earth, you do discover that there actually is a relative plane that may correspond to the plane of the ecliptic, but rather than it being planets, it's stars. And one of the most prominent of those stars would be the dog star, as it's known, Sirius. And that's going to be another lecture sometime, getting into these cosmic geometries. But there's some very interesting phenomena associated with what an astronomer would refer to as the proper motion of Sirius, that in some ways seems to be synchronized with the motion of the vernal equinox. In any case, what we're dealing with here is this idea that there's this continuum of scales throughout the hierarchy of creation. And it not only applies to the measurement of space, it applies to the measurement of time as well. Okay, so the ancient people believed that this great year was very important in the long-range thinking and planning for human society or human civilization on Earth. Because if you have studied ancient traditions, mythology, folklore, epic tales, etc., one of the things that you discover is that these tales are filled with catastrophic events. We can turn to our own Judeo-Christian tradition and we find that the Bible has like bookends. At the front end, we talk about the great cleansing, which was Noah's flood, which wiped out the old world age, inaugurated a new world age, and that comes at the very beginning within the 4th chapter of Genesis after the creation itself. The story of Noah's flood and the great deluge is echoed throughout all traditions all over the ancient world. The Greeks had Deucalion and his flood. The Sumerians had Xisthros. The Babylonians had Utnapishtim. The ancient Vedic traditions had, who was it? Maya?
Well, Manu.
Manu, that's what I'm trying to say. Thank you, Brian. Manu. Indian legends also filled with culture heroes whose claim to fame was that they were somehow able to survive this great world flood. Now, at the other end, we see that the Bible ends with the book of Revelation, the apocalypse of St. John the Divine. So we have like bookends. We have the whole story of sacred history that's condensed down into the Old and New Testament. And at the front end, we have the destruction of the world, which presumably once happened by water. And at the end of it, we have the destruction of the world by fire. Now, if we turn to the Greeks, we turn to the Sumerians, we turn to all of these ancient cultures, the Mayans, the Incans, the Hopis, I mean, the list could go on, we find the parallel traditions, that the world is alternately destroyed by flood and by fire. Is this meant allegorically, or is this meant actually and historically? I think most scholars that have looked at this have assumed that it's merely allegorical for psychological crises, for example, maybe a birth and death situation, a crisis in the case of an individual life. We certainly know that there's probably no one who lives out a life without having some type of catastrophic event that's a personal catastrophe for you, whatever it is, a death close to you, an illness, a divorce, a foreclosure. I mean, you can make the list. There's all kinds of things that we could conceive of as being catastrophic on a personal or individual level. Well, the ancient traditions also believed that there were catastrophes that would be seen on the global level or the larger cultural level, and the timing, the rhythm or tempo of these events was totally governed by this wheel right here. A whole book has been written about this subject called Hamlet's Mill. And Hamlet's Mill is interesting because after going through like 600 pages of presenting pretty much debate-ending evidence that ancient cultures all over the world had ways of symbolizing this model of the great year, and held that this model of the great year was fundamental to their cosmological understanding, their cosmological framework of understanding. They then, though, conclude that it's really ultimately an allegory, that there wasn't actually literally and physically catastrophes that happened. Of course, they wrote this book, I think it was published mid-60s, or maybe 69 actually, a pivotal year, 1969. In 1969, there was a different worldview that prevailed. And that was the worldview that would have been totally dominant, most likely during the educational years of everybody in this room. And it's called uniformity, or uniformitarianism, which held that the history of the Earth could be completely explained. Once the Earth, however it came about through planetary accretion, nebular condensation, whatever, once the planet was there, all the forces that have worked to bring about global change have been those which we have seen and experienced roughly within the last 2 centuries or so, 3 centuries that modern science has existed. This is called uniformity. And the phrase that expresses the idea of uniformity is the present is the key to the past. So the idea is, as we look at a process going on today, we'll see a volcano erupting, we'll see lava coming out, we'll see it cooling and forming a very distinct type of rock, a basaltic rock. Very distinct. Visually it's distinct, chemically it's distinct. And then we can go and we can look at ancient rocks and we can see that exact same kind of rock and presume that it had the same origin. We can watch a flood come down a river and erode a channel and create new deposits. And then we look at those deposits and discover that they're layered and that those layers tilt downward in the direction of the water flow. Then we can go and look at an ancient rock, and we can see that in that rock there's the grains that were once sand grains. They're layered and they're tilted in the same way, exactly. So from that we can conclude, well, this once represented a river. And look at this. If we look at the strata, we'll see that here's lots of thin strata, probably representing the annual flow, which ebbs and flows. You know, all rivers do not have a uniform flow throughout the course of the year, especially in the northern climates where we have snow. Rivers are, much more voluminous during the spring than they are, say, in the late summer. And of course, as the water is more voluminous, it's carrying more sediment. That sediment will build thicker layers. Now, if, for example, there's a flood, every 10 years or 100-year flood, well, that flood produces greater erosion. And if you look at layers, you'll see thin layers representing normal erosion, and then you might see a thick layer. And you can then go from that. Well, we've seen exactly this. We saw this flood on, back when we had Hurricane Ivan. Hurricane Ivan dumped rainfall on northern Georgia that they estimate was probably a 100-year flood. And if you go to all of the creeks and rivers in northern Georgia, you can still see the evidence of Hurricane Ivan. If you walk down here to the Clyde, if you go down to the Clyde Shepherd Nature Preserve down by South Fork of Peachtree Creek, where I frequently walk, the floodplain down there, you can still see the sand deposits. If you kick away the vegetation, you'll still see the sand deposits that was spread all over the floodplain back when Hurricane Ivan came through, which was, what, 2004 maybe? Or 2004, I think. Of course, it's slowly being recycled, and as the plants are growing, it's going to get harder and harder to see that sand. But there will be places where one could go probably and dig a trench and look and see that sand layer and go, oh, 2004, that was Hurricane Ivan. Okay, well, going to the geological realm now, what we have discovered is that the old model, like I said, the old model was that everything happened uniformly, and that it was unscientific to go to explanations that were different or out of scale with the things that modern scientists had seen and measured with their instruments or duplicated in the laboratory and so on. And it was considered that anybody who postulated the reality of a catastrophe, if it was anything beyond just a local or a regional catastrophe, was considered a crackpot. Certainly if somebody started talking about global catastrophes, they were considered to be a crackpot. Now, this paradigm of uniformity was what was inculcated as the cornerstone of geological thinking up until the 1980s. So anybody who learned anything about Earth history prior to 1980s would have learned about this idea of uniformity, or also could be called gradualism, that everything happens gradually. Again, there might be a local event, there might be a flood, there might be a volcanic eruption, there might be an earthquake, but it's merely a local event. There's no such thing as a global catastrophe like the ignorant, pre-literate, unscientific, barbaric ancestors believed that there was. They all seem to concur that there were, in fact, really such things as great global catastrophes. Well, of course, geological science has gone through a complete upheaval since the 1980s. The upheaval from the 60s to the 80s was the advent of global tectonics. It took, they fought tooth and nail against the idea that there was could be any movement at all, that the plates over the Earth was first proposed in the 1920s by Alfred Wegener, and everybody said he was a crackpot because he said, well, the plates move. The plates move over the mantle. And they said, you're crazy, you're nuts, get out of here. Go up to Greenland and disappear, and that's exactly what he did. Well, so by the 1960s, though, everybody had agreed that, yeah, all the evidence suggests that the plates actually do move. And this was going to be a huge revolution in the thinking of Earth science, in Earth history. Well, the thing was, though, is those movements were slow, maybe 2 centimeters a year, about this much, maybe a 1/4 inch, 3/8 of an inch. You know, at the mid-Atlantic ridge, the plates are spreading apart slowly, a couple centimeters a year. As the North American plate pushes to the west, it bumps up against the Pacific plate, and as it bumps, it does this, and it wrinkles up, and it forms the Sierra Nevadas, then the Basin and Range, and then the Rocky Mountains. And so the idea there is that those mountains would have been uplifted, essentially at a rate that could be commensurate with the spreading rate of the plates. Problem is, though, you've got other studies that have been looking at the erosion rates. And as you take a piece of land and start lifting it up, the higher it gets above sea level, the faster it erodes. Once you get, up to 7,000, 8,000, 9,000 feet above sea level, you now get this freeze-thaw cycle. It can be tremendously destructive to rocks. Water can get in cracks in rocks. It freezes, it swells, breaks the rocks off. The rocks tumble down into the valley. But what's interesting is if you look at pictures of mountains, the Rocky Mountain, or if you've ever traveled through mountains, what you'll see is that mountains are many of them, like the Canadian Rockies, you can see overthrust faults where you have a slab of rock a mile thick that's been pushed 30 or 40 miles up and over the rock that it used to be on the same level with, right? And if you look at the sharpness of mountains, for example, if those mountains were being raised slowly at the rate of seafloor spreading, the erosion rate would be roughly commensurate with the uplift rate. In fact, geomorphologists who study rates of erosion have estimated that it would take at the current rates of erosion, it would take 10 million years to 12 million years to wear down the entire North American continent to sea level. 10 to 12 million years. Geologically, that's not a long period of time at all. But of course, if we look, we see that North America is not worn down to sea level. It hasn't. In fact, there are these fresh, broken-looking mountains that you can see. Anybody who's traveled through the Rocky Mountains or through the Sierra Nevadas can testify to that, to the mountains, and how sometimes they look like they could have just basically been upthrust yesterday. Well, see, this is the kind of thinking orogenesis is definitely thought of as being a slow process. But if it was a slow process, rocks, mountains would be worn down almost at the same rate that they're being uplifted. We could cite many examples. 1980, pivotal year. What happened in 1980 that was in its own way more revolutionary than the idea of plate tectonics? And I will call on Brian again. No, not Mount St. Helens. That was significant, but not globally significant. In the scientific community, what happened? There were 3 papers published. And they all took a mystery, a scientific mystery that had puzzled paleontologists for a couple of generations, and suddenly came in with a new catastrophic theory: the extinction of the dinosaurs. 3 papers, all in 1 year, came out. Now,
theory about the asteroids.
You got it. You got it. That's exactly right. Walter Alvarez and his team discovered, looking at a sedimentary layer in Italy, that there was below which dinosaur fossils were in abundance and above which there were no dinosaurs. They looked at that and were trying to calculate how long did it take to for the global ecosystem to transition from dominance of dinosaurs at the top of the food chain to no dinosaurs at all. How long did that transition take? The assumption was within uniformitarian framework that it might have taken a couple of million years, or 10 million years, or 20 million years, or even longer. What they did, and here was their insight. They thought, okay, you know what? We know that every day Earth gets dusted by cosmic material. Platinum group metals, rare earth materials, platinum group metals such as iridium and beryllium and zirconium that filter down from space and go and get reworked, recycled into the topsoil. And they thought, okay, what we're going to do is we're going to look at this boundary layer, which was very distinct because the rocks below it were distinct from the rocks above it, and these 2 different kinds of rocks were separated by this 2-inch thick white layer. He says, well, we're going to take a look at this white layer and try to determine what it was, or how long did it take to transition between those 2 types of rock deposition. Well, we're going to go and we're going to look at the amount of iridium, because if we can say that X amount of iridium falls on the surface of the Earth each year, we should be able to get an idea of the length, the duration of the transition. Well, when they looked at that layer, they discovered that the amount of iridium was many, many times greater than in the rocks above or the rocks below. In fact, it was so great that they thought something unusual happened here. Well, what in the world could it, now is this something unusual that just happened here locally, in this outcrop in Gubbio, Italy, or would it happen other places? Well, what they did was they started contacting their colleagues in Denmark, New Zealand, other places in Europe, North America, and they said, would you guys go back and take another look at that KT or Cretaceous Tertiary boundary and see if there's an iridium spike? Well, what happened is, as they did this, everybody discovered, wherever they looked around the planet, that there had been a big dose of cosmic material that had influxed to the Earth right at that horizon. Now, the significance of this is, it's very simple. When these guys said we know that iridium dusts to the Earth, sprinkles to the Earth a little bit every year. But what is it that could cause this enormous spike of iridium to suddenly show up around the whole planet? Well, they knew from their astronomy background and talking with astronomers that the one place where abundant iridium was found was in meteorites and asteroids. So they were then able to come up with a theory that said, Well, an asteroid could have been the most likely culprit for depositing this iridium layer around the Earth. Of course, this ignited, and at the same time, two more papers came out, one proposing a comet, and another one basically proposing a variation of some asteroidal type event. They all came out in 1980. Okay, with three papers, if it was just one paper, it might be possible for orthodoxy to essentially ignore it. But three papers coming out, all proposing variants on the same idea, was very difficult for mainstream science to think about. Now, it's interesting that geologists being schooled in the doctrines of uniformity, very resistant to the idea because they're going, no. We know that everything happens gradually. And what you're talking about is some kind of a global catastrophe, and that's totally unscientific. Paleontologists, very resistant to the idea because they were imbued with the idea that, well, we know that the dinosaurs were extinct, but they went extinct because they slowly evolved into other higher forms. They must have evolved into various forms of mammals and birds, and what you're saying implies that somehow they were just suddenly erased. So the geologists and the paleontologists were very resistant to this idea. Who do you think was more receptive to it? Which group of scientists would have been more receptive to the idea? Astronomers, yes. The reason is because by 1980, you now had planetary geology that by 1980, we learned a lot about the other surfaces of the other planets, including the moon. Prior to the Apollo program, half of the scientists believed that the craters on the moon were volcanic. Well, post-Apollo, we knew, and I won't get into the whole evidence that conclusively proved that all of the craters on the moon were in fact impact produced, or 98% of them anyway, were produced by violent collisions between the moon and things out in space, asteroids and comets. Okay, so astronomers were aware of that. They had factored this into their thinking, that there were literally several million craters on the surface of the moon. Also, they were beginning to look at our neighborhood in space and contrasting to the older view of there essentially being nothing out there in space except perhaps solar radiation. They were now beginning to realize that near-Earth space was really a highly densely populated region, and that there was a lot of stuff there besides the planets zooming around the sun. So they had put these two pieces of information together, and some of the more advanced thinkers were already beginning to ponder, well, you know what? If we've discovered from our closest counts that there's several million craters on the moon, and it's a simple extrapolation from physics to realize, based on the Earth's larger size and the fact that it's 81 times more massive than the moon, that the Earth should be have 80 times more impacts than the moon displays. What does this imply? Well, it implies the idea that Earth's history may be profoundly catastrophic. See, so astronomers, particularly the planetary geologists, the deep space astronomers, they weren't concerned with stuff like that. They're out there looking at galaxies and metagalactic clusters and so on. They're not too concerned with, what's the relation between space, right here, between us and Jupiter, for example. But the planetary geologists, those guys, they were having a rather sobering wake-up call because they were beginning to find out. Okay, so now, over the next basically 10 years, you have a controversy raging between two camps, the gradualists and the catastrophists. And this was like a revival of the original controversy that existed at the dawning of Earth science back in the 17 and early 1800s. You had catastrophists and you had gradualists. The gradualists won. And you know why they won? They won because what they did was they focused on the small group of geologists that tried to fit their catastrophic scenarios within the six-day creation biblical framework. And because that didn't work, essentially it's very similar to some of the global warming controversies that are going on right now. If the climate warms and humans have put CO2 into the atmosphere, then it follows without any other consideration that slight enhancement of CO2 in the atmosphere is what has provoked the warming. never mind other possibilities. And there are multiple other possibilities. Well, in the dawning of Earth science, you had this controversy where you had catastrophists. The catastrophists broke into two camps. One camp that was trying to put the framework within the 6 days of creation and say all of the evidence that we see in the field for catastrophic events is Noah's flood. Then you had other groups, another group that said, well, there's catastrophism, but we don't need the Bible. It's just there in the field. It's in the rocks itself. We don't need to go to the Bible. The other camp was the gradualists. And basically the gradualists won. The uniformitarianists won. By the late 1890s, pretty much all of the catastrophists had pretty much died off. And going into the 20th century, the prevailing absolute dominant paradigm was strict gradualism. You see, all of that began to change in 1980. Throughout the course of the 1980s, here's what happened. More and more evidence is being discovered around the planet for the reality of this catastrophic event that terminated the era of the dinosaurs. Simultaneously, they're discovering other horizons, geological horizons it's called, strata, that have the same type of signature, the same type of fingerprint, which again is consistent with the idea that it didn't just happen once, it happened perhaps many times. Now at the same time, we are getting higher tech means of looking into the ground. Geologists are developing ground penetrating radar, things that allow us to look under the surface and see what's there. Well, what happened was suddenly geologists began looking for evidence that there had been cosmic events. And guess what? We begin to find it everywhere, everywhere. Dozens and dozens of what are called, well, a crater is the classic bowl-shaped, but some of them were old and eroded or filled with sediment, so you didn't have the classic bowl shape, so they called them astroblemes. An astrobleme literally means star wound. Well, as the geologists have been looking now for 29 years, they've discovered that there are hundreds of astroblemes, and the areas that they've looked are very concentrated. For example, in areas where Australia, for example, has a lot of astroblemes. Why is that? Because Australia is desert. And so you haven't had a lot of erosion there and a lot of vegetation and so forth that would conceal or obscure the astroblemes. The oceans. See, the hundreds of astroblemes that have now been discovered, maybe 10% to 15% of the land surface area. Well, what this translates into is that there are almost certainly thousands of astroblemes on the surface of the Earth. Well, now to get it back to this. As we begin to look and we begin to study and learn about the timing of these events, and of course, in the early 90s, they did in fact discover that there was a gigantic astrobleme under the Yucatan Peninsula that was exactly the requisite age to correspond with the demise of the dinosaurs. And that was pretty much the smoking gun that caused most of the critics to finally throw in the towel and admit that yes, there had been catastrophes. And these catastrophes have profoundly affected life on Earth. Okay, where we have come since the 90s and going into the 21st century is that by the 21st century, dawning of the 21st century, scientists had begun to accept, scientists that studied the history of the Earth, had begun to accept that the history of the Earth had actually been profoundly catastrophic. What they were not yet doing was making that connection with human history on the Earth. Now, in the 80s and 90s, there was a British school of neo-catastrophists who did focus in on the idea of there being, it's one thing to say, well, there was a catastrophic impact 65 million years ago, and what, we're done?
No, we need a break.
Okay, we can do that. I will let you have a break, because we don't want any catastrophes. Thank you. British School of Catastrophists who, who did conjecture about the role of cosmic events in human history. And see, this is where it comes back to us and what we're doing here, and as we try to think have any kind of a realistic conception of the future. I mentioned earlier that the cornerstone phrase of the uniformitarian worldview is that the present is the key to the past. And I digressed and I explained how, for example, by looking at the formation of a basaltic rock, or by looking at sedimentation, or any number of processes that are going on at present, one can understand how similar processes would have operated in the past. Okay, so the phrase that describes that approach is the present is the key to the past. And that was considered to be a major step in the evolution of thinking about the history of the Earth back in the 19th century when that was first proposed by a man by the name of John Playfair. Well, I like to propose now that an extension of that phrase, which would be that as the present is the key to the past is the key to the future. And if we want to have any kind of rational, reasonable, or realistic conception of the future, we have to look at the past. And again, the idea can be a very fruitful idea, this idea of scale invariance. You can picture, try to do another mental exercise here. A person whose memory only goes back, let's say from the present, goes back 2 months. So their memory only goes back to June and they have no conception of anything that happened before June. Well, clearly then, they're not going to have really a notion of what winter's going to be like, are they? Not until they've lived through and experienced a winter and seen the return of the spring. Now, of course, here in Georgia, it's not quite as dramatic as where I grew up in Minnesota, where a winter and a summer are very, very different. You know, if somebody whose memory only went back to June, they would have no conception of snow or snowfall, would they? All they would be able to do is find out indirectly by, reading accounts of snowfall and so forth. Well, you see, mankind is suffering from collective amnesia. And this, I think, is one of the most critical insights that we modern people can realize. Mankind is suffering from amnesia. Now, I've talked about this for those of you that have heard my talks before. I always like to point out the fact that we now have hard evidence from the paleoanthropological realm, skeletal remains, bones of modern humans that date between 150 and 180,000 years. Our written record, 4,000, maybe 5,000 years old. Our written record is only less than a 20th of the span of time that we know modern humans have been on the planet. What happened prior to the beginning of recorded history? See, that is a mystery to anybody who considers how it is that it took so long for human beings with presumably intelligence comparable to our own today to figure out that they could actually create a culture, a civilization, and that learning could be an acquired process that could be handed on from one generation to another. In fact, I don't think even Stone Age cultures, of which there were many still existing into the 20th century, had ways of transmitting knowledge from one generation to another, what we consider to be Stone Age cultures. But how is it that for so many millennia, hundreds of millennia, there was no acquired knowledge that was passed on, and only between 4,000 and 5,000 years ago do we begin this thing called recorded history? Well, if you go and study the history of philology, what you'll discover, pardon me? Okay, the question was, what about language? Well, what you'll discover is that most of the language trees, the branches of language on the earth today, essentially trace back to a series of bifurcations that are usually dated at 10,000 years ago, about 8,000 BC. And what that implies to me, because of what I know about the history of the earth, that there were profound changes that occurred between 10 and 12,000 years ago. I think that the dispersal of languages, along with the domestication of animals, the formation of settled agricultural communities, the building of the first cities at about 6000 BC, all of these things I think of as evidence for the rebooting of human civilization after its catastrophic termination between 11 and 12,000 years ago. And once we begin to understand the scale of the events that have occurred since we human beings have been here on the planet, the question that's raised is not so much how it is that traditions have been lost, but how it is that we're actually still even here and not having gone the way of the woolly mammoths and the saber-toothed cats and the glyptodonts and the mylodonts and all the rest that aren't here anymore, that were here for most of the time that humans have been here. Yes?
What tragedy or catastrophe do you think happened?
Well, a geologist would point to the fact, what catastrophe? The question was what catastrophe or what event do I think happened during that period of time? What the ultimate cause was is a mystery. Although I think there is now, in the last few years, some new evidence that emerges that points to a culprit. But we can certainly see its secondary consequences. From roughly 26,000 years ago till about 12,000 years ago, the planet was in the grip of a deep ice age. There was an ice cap as big or bigger than the one that now covers the South Pole, covering 2/3 of North America. Think about that. If you traveled north from here, you wouldn't have to go far across the Ohio River. Once you crossed the Ohio River from Kentucky into Ohio, you were in an ice cap. Where New York is now, you had ice a mile thick. There were no Great Lakes. Sea level worldwide was 400 feet lower than it is now, 400 feet lower during the Ice Age. I could go on and on with the extraordinary differences between the planet then and the planet now. In fact, I will actually show you some slides that's going to convey some of that, I think, to you.
Wouldn't have people just gone into the tropics and around the equator and held out there?
That would be a good strategy, yes. Although we do know that there were people living right up to the margins of the ice sheet. The Clovis people, some of the first inhabitants of North America, were hunting some of the large extinct game animals right up to the edge of the ice sheet. Just like Inuit Eskimos will hunt seals right up to the edge of the Greenland ice sheet, and caribou. There were Clovis people that were actually living, hunter-gatherer communities living right there adjacent to the ice sheet itself.
What was it that made us almost extinct? What was this? Was it the ice sheet or something else that happened?
What was it that almost made us extinct? Well, by implication, what I've been saying is that it was something from outside. It was a cosmic event that caused a tremendous global transition. Essentially,
Is that the Yucatan one?
no, that was the Yucatan one. She asked, was that the Yucatan one? Let's try to get a time framework. The Yucatan was the end of the dinosaurs. That was 65 million years ago. Long before humans, long before humans. The event that I'm talking about was only 10,000 or 12,000 years ago. Well within the span of time that humans have been here.
One off Australia.
Pardon me?
One off Australia?
Um,
Not Australia, but
Madagascar. I'll get to that if we don't run out of time. This is a wheel. Can we do the lights so people can see, or maybe you can, let's see if we can. There we go. Here's a model of the great year. This is that same cycle of 26,000 years, and essentially that vernal equinox has been shifting. It's been shifting through from here, circling around. Notice I have 0 years before present. And I have 25,920 years before present. That's the full span of the cycle. And if you look at this, here's a cross. Remember on the first graphic I showed you, there was a cross. The equinoctial line, the solstitial line. They're turning at this cycle of 25,920 years. Now, I have a graphic here. Let me see if I can find it. relatively quickly, because clearly we have evidence that something happened. All right, before I do that graphic, here's the thing I wanted to show you, to convey to you. Now here's where it would be great if we could get some lights down, just so that this map can be seen. Is that possible? All right, let's take a look here. Now what we've got here is a map of the Earth as it exists today, and if we zoom in a little bit, we can see that around all of the continents, this light blue area, which is the continental shelf. Okay, the continental shelf is generally less than about 500 feet below sea level. Now, during the Ice Age, you know, this whole thing down here on the bottom, that's Antarctica. This is a transverse Mercator projection, so the bottom is stretched out and highly distorted and out of scale. But you have the Antarctic ice cap, which is a continental landmass surrounding the South Pole, a continent surrounded by ocean. At the North Pole, we have an ocean surrounded by continent. So we have a huge ice mass accumulation at the South Pole and not much ice accumulating at the North Pole. During the Ice Age, essentially what we had was an accumulation of ice over northern North America and northwestern Europe, and the total volume of that ice is estimated to be between 6 and 7 million cubic miles. Bigger than the amount of ice at its maximum bigger than the amount of ice that now mantles the South Pole. Where did all that ice come from? Ice forms from water. Where did the water come from that formed the ice? Where's the obvious place? The oceans, right? Well, if you pull 7 million cubic miles of water out of the ocean, what do you think is going to happen to the ocean level? It goes down about 400 to 450 feet worldwide. When it does that, it exposes the continental shelves. So now the next image will give you an idea of what the map looked like. It doesn't show the ice cap, but it does show relative sea level during the Ice Age. And in order to appreciate how drastically different, let's take a few closer views. Here's North America. Everybody, how many of you in here have heard of the Bering Land Bridge? Okay, good, good. The Bering Land Bridge. What's this to hit somebody with? All right, pay attention. If I see anybody sleeping, right there is what's called the Bering Land Bridge. Now, if you'll notice that light blue area, you're going to see that the light blue area is actually bigger than Alaska. Now, watch what happens when I drop sea level 400 feet. You see what happens? Suddenly North America and Siberia become part of the same continent. That's quite interesting. Look at Florida down there. Now actually, this map only drops sea level 350 feet. During the largest glacial ages, we could drop it another 100 feet. So the effect would even be more pronounced. Look at Florida when I back up. How different. Look at the maritime provinces up here. Hudson Bay, of course, disappears. You know, here's Hudson Bay. Hudson Bay being a remnant of the great ice mass that once mantled North America. Look at Indonesia, Indochina. I don't know how good your geography is, but there's Australia. You know, Vietnam is right here. Sumatra is right in here. Watch what happens when we drop sea level 350 feet. Thousands of square miles of land appear. So what, of course, happened to that land as sea level rose? It was drowned, wasn't it? Let's look at northwestern Europe. British Isles right there. See, there's England, Scotland, Ireland, Spain. Up here is Scandinavia. You have the Baltic Sea right there. Out there is Iceland. Now let's drop sea level. Watch what happens to the British Isles. What British Isles? There were no British Isles in the Ice Ages. You could have walked right from the continental mainland right out, and the British Isles were just basically a series of hills. Okay, now I'm trying to show you this so you can begin to appreciate how revolutionary were these changes. Now, in the old gradualistic paradigms, this transition from the full glacial age to the interglacial age was something that was imagined to have taken tens of thousands of years, 50,000 years. Of course, we now know that it was something that happened over just a couple of thousand years. Well, to try to compress this amount of change into a couple of thousand years isn't easy. And we're left with a problem. The problem is what mechanism could actually cause so much ice to disappear so fast and sea levels to come up so fast. Interestingly, right in the middle of this process, about 11,600 years ago, if you guys have read your Plato and know the story of Atlantis, that's precisely the date that he gives for the sinking of Atlantis. In fact, oceanographers and marine geologists have identified that the most rapid period of sea level rise, post-glacial sea level rise, was right centered at 11,600 years ago, which coincides precisely with Plato's timing. Well, so I want to show you a graph, because we're not going to go for 2 hours, although we could. I'm going to show you a graph that links what we now know about catastrophic events during the time that humans have been here.
You show that one that just showed the polar ice cap over most of the Earth?
Yeah,
It was number 31. It was just up here.
well, let's do. I think that's an excellent one to show. In fact, I did want to actually show that. Let's open, and we'll look at what, essentially, this is the current situation. You can see North America, there's Greenland, where there is an ice cap over Greenland because it's built up over a land mass. But there's no ice cap over North America. There, if you look close, there's the Great Lakes. I'll zoom in here. Okay, if we look right down here, you got to look close, but there's the Theosophical Society right there. Okay, now let's turn the cosmic wheel back half a cycle, half a great year ago, 13,000 years ago. And guess what? The winter of the great year. He's using the analogy of the seasons, right? There's a summer and winter of our annual year, the trip of the Earth around the sun. There's a summer and a winter of the great year, but the summer of the winter of the great year could be thought of as a glacial. An interglacial age would correspond to the summer, a glacial age would correspond to the winter of the great year. And that right there represents the winter of the great year. 6 million or more cubic miles of ocean water taken, lofted out of the ocean basins by the hydrological cycle, precipitated out as snowfall over the continents, but that snow doesn't melt. Can you imagine, this is what it's like. Going into a glacial age would be like going into winter, but instead of the winter being 6 months long or 8 months long, winter is 15,000 years long. That's what it's equivalent of. And that's what you've got right there is 15,000 years of accumulated snowfall. In fact, it's actually more than 15,000 years of accumulated snowfall, but we know that 30,000 and 40,000 years ago, where that ice is, there were forests growing. So obviously we weren't in an ice age when there were forests growing on the shores of what is now Hudson Bay. The problem is that the rate of accumulation so far exceeds what we would consider normal for a regular snowfall, is that there's another mystery proposed there, is the initial high rate of ice accumulation. An extraordinarily fast accumulation of glacial ice. Yes, back there.
What was the Great Basin Sea?
We're going back to the Great Basin Sea. I think we've got to go back to the Mesozoic. I mean, we're going back 100 to 200 million years ago. So that would be beyond the framework of what we're looking at today. If you want to stay here maybe till like 11 or 12 o'clock tonight, we could work our way back.
Randall, instead of having global warming, are we just going into the great summer?
Well, interesting question. Instead of global warming, are we going into the great summer? I would say that it's actually far more likely that we would be headed for an ice age than a warming. And let me show you this graph here, because I think this graph, in fact, the very next graph, will convey to you what I'm talking about. This is sea surface temperatures, this graph right here. And if we look at this, let me explain to you what we're looking at. The present is 0, and over here means 400,000 years ago. And this is based upon studies of the bottom of the ocean, because basically marine geologists and biologists and oceanographers and so forth, by looking at the kinds of creatures that were in the ocean, died and whose remains then fell to the ocean floor, the kinds of dominant life forms in the ocean is temperature dependent. In fact, there are like coiling creatures called foraminifera. The coiling directions of foraminifera are opposite from cold water to warm water. That's a very, very distinct proxy or indicator of temperature shifts in the ocean water. There's a whole host of these what are called proxies by which the ocean temperatures can be reconstructed. Let's look at this. Look at this graph right here. Now, what I'm going to do is the 0 point of this graph, sorry Brian, I'm going to have to walk in front. The 0 point is right here. This represents now. That little peak that's greater than now is a period of time post-ice age that was called the climatic optimum. It lasted from about 9,000 to about 6,000 years ago. And if anybody ever tells you that the 20th century is the warmest century on record, don't believe them, because it was actually considerably warmer during the climatic optimum. Okay, now look at the trend of this graph. I'm going to throw a red line across it representing the modern temperature. And what do you see? The troughs represent full-blown glacial ages. The peaks represent interglacial ages. Now, if you were looking at this graph and we're going to predict, assuming something hasn't completely interrupted the pattern, the succession here, what would you predict at some time in the future based on this graph? Yeah, doesn't it look like if you follow any one of these peaks, what happens is after the peak, it declines, and basically we're talking about a 10 to 15 degree Fahrenheit difference in temperature between here and here. And that's the difference between an interglacial age and a full-blown glacial age. During the glacial age, Georgia had a climate similar to what you would find in Canada today. Georgia would have had full snowfall every year with spring thaws and so forth. In addition to that, there were woolly mammoths and mastodons and saber-toothed tigers living in the jungles, in the forests of Georgia, plus all kinds of other strange and exotic, very large creatures that all disappeared during this transition. Okay, so based upon this graph, one would probably think that at some point an ice age might actually be more likely. Now, I have been studying the subject of paleoclimatology for many years. Yes, and that's going to be my next slides here that I'm going to pull up so you can see. This is an older graph from the 1970s. The graphs that we have now are actually much higher resolution and show a lot more detail. So, however, the general trends that are indicated in that graph are still valid. I mean, the general trends from interglacial to glacial, and if you look at it, does seem to be a certain rhythm or tempo to these changes, doesn't there? I mean, that showed up unmistakably on the graph. Okay, so I'm going to scroll down here. Is everybody seeing these? Am I going too fast? Well, this will all be, all right, here we go. So here's this graph that we were just seeing. And now I'm going to look at a higher resolution graph. This is based on oxygen isotopes. I won't spend any time explaining how it works, other than to say that this is another one of those things called proxies, which is a way that scientists can reconstruct past temperatures. And let me explain to you what we're looking at here. When it says relative oxygen isotope ratio, It goes minus increasing that way and increasing this way. Basically what that's saying is that you've got two types of oxygen, 16 and 18. 18 is a heavier isotope. During warmer times, the heavier isotopes, because of the more energetic hydrological cycle, they are evaporated out of the ocean and precipitated out over land. When the temperature warms, the heavier oxygen gets introduced into the hydrological cycle more readily. When the temperature cools, energy is reduced that's available for pumping the hydrological cycle. So at that point, the lighter weight oxygen, the oxygen 16, is preferentially evaporated, the heavier oxygen left behind. So you have this correlation between the amount of oxygen 18 in the ocean and the amount of oxygen 18 in the ice. During the warmer times, oxygen 18 in the ice increases. During colder times, oxygen 18 decreases. Shifting to the left is a decrease, shifting to the right is an increase. Shifting to the left means a decline in temperature. A shift to the right means an increase in temperature. This is taken from ice cores extracted from the ice sheet over Greenland, which is 2 miles thick. It took 5 years for two teams, heroic scientific enterprise from 1988 to 1993, to drill these core samples. A European team and an American team, they went to the center of the ice where it was the thickest with the least distortion, the greatest preservation of the record. They drilled 2 cores down to bedrock, took those cores out, and they began to look year by year, because just like tree rings, each year preserves a layer. The snow falls, it gets packed in, it preserves a layer. In those layers, you have oxygen isotopes, you have gases trapped, such as CO2, such as methane, you have dust, you have soot, you have organic material, and all of this stuff will allow scientists to determine what was going on in the environment when that layer was deposited. If you're following this so far, this is the present. This is at 1,500 meters down, over 3,000 feet. The timing, each one of these is 1,000, 2,000. This is 10,000 years, if you can see this right here. My podium is not in the way. 10,000, so when they've gone down 1,500 meters of ice, that's the ice that's accumulated in the last 10,000 years. Yes?
How did they determine the age?
You can count the layers. Every year there's a layer put down. You can go in there and you can 1, 2, 3, 4, and you can just count them, just like you count tree rings to know how old a tree is. Got it? Okay. A few of the events. Eric the Red visits Greenland right here. Birth of Jesus right here. Start of the Pyramid Age right here. This was actually supposed to say the building of the first cities. Okay, just after 10,000 years ago. Now look at, first thing I want you to call your attention to when you look at this graph is this. Do you see any time in that graph where the temperature is smooth, where it's not changing? Does anybody see any period of time up there where the temperature is not warming or cooling? No, you don't. Now, what magnitude of temperature changes are we talking about here? I'll give you an idea. Right here at 82, between 82 and 8,400 years ago, there's a cold spike. It lasted about 2 centuries. Very interesting story there, but I'm not going to get into it. But that event is about a 5 degree cooling. 5 degrees. Now, if you read your global warming literature, the consensus is that since 1850, the global climate has warmed by 0.7, 7/10 of 1 degree, right? What they're projecting is that it's going to warm by another perhaps 2 degrees in the next century, meaning a total of 2.5 or 3 degrees of warming. However, that's controversial, and I would love to give a whole talk just on the controversy of global warming, because not to digress on that, and I'm only going to say 2 sentences on that. What you hear from media is that there's a consensus and the debate is over, and that's complete hogwash. The debate hasn't even begun yet on the nature of climate change. But as long as the UN continues to pump $4 billion a year into global warming research, and that's where all the grant money is, people are going to, essentially what they have done is they've come up with a a budget of $4 billion a year and have hired 2,500 climate scientists to say that there is a consensus of on the issue of global warming. And if you know, sometimes people initially are going, wait a second, I thought, you know, that's well established. It's being taught in all the universities now that the debate is over. Of course, science was never about consensus at all. It's about debate. It's about skepticism. And if you gave me 2 or 3 hours, I could lay out the whole spiel and I could deconstruct everything Al Gore said in The Inconvenient Truth, and I would love to do that. But that's not what we're here to do today. However, part of what I'm going to show you is of relevance to the whole question. If you look at that, first thing to notice, there is no period where climate is stable. There's no, what do you put in here and say, this is the norm. This is what climate is supposed to be and everything else is abnormal. There's nothing up there to do that. Now what I'm going to do is I'm going to take that same graph going back 10,000 years that I'm showing you right here. I'm going to turn it on its side. Let's take a good look at this and see if we see any trends, anything going on in this graph. Now as we look at it, there's 10,000 years ago and here's now, right? To help us get a reference, I'm going to put a reference line in there. And you'll notice that within the last few, look, there's 2,000 years, 3,000. You can see that around 2,000 years, starting about 2,000 years ago, most of this, of the up and down oscillations are below the line, right? Can you see that? If you go back, you know, 7, 8, 9,000 years, you'll see that a lot more of it is above the line. That's pretty clear. You can see that, right? Let's see if okay, I'm going to drop the line a little bit. Now you can see what I've done is I put that line, where it stops right here is the modern temperature. So what do you see when we extend the modern temperature back? Remember I said there was a climatic optimum when temperatures were warmer than they are now? Can you see it? It's right here. After the Ice Age, this is what we had. The planet enjoyed a period of balmy 3,000 to 4,000 year period of warmth in which the climate was warmer than it is now. Now here's the other thing that I think is very important that's being left out of the discussion on anthropogenic CO2-induced climate change, is that you've probably all heard, because mainstream media has trumpeted this, that the global warming is supposed to cause increased storms, increased severities, more tornadoes, bigger hurricanes, greater oscillations in the year-to-year and decade-to-decade temperature swings and so forth. Now what do you see when you look at the amplitude of the oscillations, the temperature variations up and down? What do you notice happen to the amplitude as the temperature is cooling? They're getting greater, aren't they? In fact, this is completely opposite to what mainstream media has been telling us is supposed to happen. And in fact, I mean, I could show you a graph of cyclonic energy for the last century, and what you would see, in fact, think about this. Now here we are, we're what, 6 weeks into the hurricane season? How many big hurricanes last year? How many big hurricanes the year before that? Now we did have 2004, big hurricane year, yes, but we can go back every 10 or 12 years for 200 years and discover that there will be a year or two of intensified cyclonic energy. This has had nothing to do with CO2 input into the atmosphere, at least human CO2. Okay, but here's the thing I want to get to, and I want you to see, because this is where it gets profoundly significant and important. I'm going to go back, and here is the graph from where we first see it. And again, to put it in perspective, proposed warming for the last 150 years, 0.7 degrees, 7/10 of 1 degree. 5 degrees, that spike right there is about a 4 or 5 degree warming. So you can see, you know, 6 to 8 times the magnitude of the projected warming that has occurred from the mid-19th century for the next 50 or 100 years. Now, when we get down to here, we're getting back into the Ice Age. And something very interesting happens, and I'm going to show you, and I hope now, hopefully now you're going to appreciate that our planet has been subject to some much more extraordinary vicissitudes than what we've experienced in recent times. Watch and learn. Aha. Now see, I find it significant that Al Gore is not talking about this, but he needs to be, Because any discussion of climate change that leaves this out, I think is woefully incomplete. And what is going on there? Well, if you want to talk about a global warming, I'll show you two spasms of global warming. Here's the first one, and here's the second one. Now, what is the span of time? We're looking here at 15 to 20 degrees change. What is the estimated time over which that magnitude of global temperature change took place? Oh no, 10,000 years is the whole graph.
Looks like about 100 years.
Would you believe 3 to 5 years? 3 to 5 years. Do we know what mechanism was responsible for that? No. Well, I do, but mainstream science doesn't know yet. I've already told you.
Oh, really?
Yes. Okay, well, sort of, yes. You've been coming to my talks, so you have an idea of where I'm going with this. Pardon me?
Volcanoes, if they threw up enough dust, could create that effect.
Volcanoes, yes, if they threw up enough dust, and that has been proposed, and it's an interesting idea. The problem is that the evidence of that magnitude of volcanic eruption doesn't exist. There were volcanic eruptions. I could show you slides that I have taken where I have found the layers of volcanic ash. There were major volcanic eruptions. Well, let me say this, volcanoes did contribute, but the volcanoes were primarily a response. If you think about the slides I just showed you with this enormous mass of ice over Canada, perhaps as much as 3 miles thick. I mean, picture the skyline of Atlanta, and you're looking at the Bank America building. That's 1,060 feet tall, right? So to get 3 miles thick, how many of those? You have to have 15 of those stacked on top of each other, for crying out loud, to get the thickness of the ice. Now, what does that do to the land under it? It pushes it. It's like what's happening to those chairs as you're sitting on them? Okay, isostasy. It's when you sit down on those soft cushions, the cushion goes down, doesn't it? What happens when you stand up? You just sat down. What happened to the cushion when you sat on it?
It went down.
What happened when you stood up?
It raised up.
Okay, that's isostasy. What happens when the glacier mass grows? The crust of the earth compresses down. It pushes down into the mantle. And the mantle, which is molten, now gets pushed to the side, right? Now, when you have unloading, here's this tremendous hundreds of trillions of tons of weight being removed. Where is it going as it melts? Back into the oceans. Okay, now what happens? Here's the continent rising after the ice is gone. The weight is being transferred back into the oceans. You have this tremendous mass transfer going on the surface of the earth. What do you think is going to happen to the chambers of magma and so forth that are found throughout the lithosphere with these changing pressures and tensions that are going on? It's only natural that you're going to have enormous volcanic eruptions going on with this concomitant enormous readjustment of Earth's tectonic plates as a result of this glacial unloading, particularly with it occurring as rapidly as we now know that it happened. Yes, Greenland has begun melting in the middle of the 19th century. And
So you're saying it's just a natural progression?
what I'm saying is, regardless of what my opinion is, the glaciers around the planet, Greenland included, but not Antarctica, have been melting steadily with some fluctuations for a century and a half. Human influence, anthropogenic influence on climate, the amount of CO2 that is speculated to have any greenhouse effect at all, didn't achieve those concentrations till the end of the Second World War. But by that time, the glaciers worldwide had been in recession for nearly a century. So now when we look at the glaciers receding, what we're seeing is that it's just a continuation of something that was going on for 100 years before anthropogenic contributions of CO2. So is it reasonable to then assume that what has been going on for 150 years suddenly is obviously, prior to human-induced CO2, glacier recession was a natural phenomenon. Why is it that we suddenly abandon the natural mechanism and say it's solely responsible, that humans are solely responsible now? Has it? Has it? This is what mainstream media has been telling you, but has it? In fact, did you know that the Arctic ice grew significantly in the last 2 years? I can show you the graph, right? Pardon me?
Since the Industrial Revolution is when it started.
Well, notice that the Industrial Revolution began about 1850. Now, if we look at climate change for the last 10,000 years, what we see is that there was an episode called the Medieval Warm Period. It lasted from 900 AD until about 1350. It was followed by what is known as the Little Ice Age. The Little Ice Age was a 2-degree cooling of the global average temperature. That's the best estimate. With the onset of the Little Ice Age, glaciers worldwide began to grow. In fact, they grew to the biggest extent, the greatest extent that they had been on the planet since the end of the Big Ice Age. Between 1400 and 1850, all the glaciers and ice caps on Earth were the biggest they had been in 10,000 years. Around 1850, at the time that the Maunder Minimum ended, in other words, the sun in 1850 began to get more active. What happened to glaciers worldwide? The Little Ice Age came to an end and the glaciers began to recede at that point. The greatest and fastest rate of recession was actually between 1850 and 1900. And then it slowed down, and then it picked up, and then it slowed down. But the amount of ice is well within the natural range. I mean, I see we're running out of time, but I could, let me just, to give you an idea here, let me show you a program that I've put together to address all of these the very questions that you're raising, because I think it's vitally important. This program right here that you see, a massive amount of information, addresses every single issue raised in the discussion about global warming that's been going on today. All of it. It's all right here. And of course, it would take me 2 or 3 or 4 hours to take you through the entire thing. But I do think it's vitally important, and over the next few months, I actually intend to look for various venues in which I can present this information so people can see what the science is actually telling us. Yes, yeah, 1811, 1812, 1811, 1812 was, at the onset of the Little Ice Age, yes. Right, well, you know.
Wasn't that Krakatoa?
Well, that was the 1811. 1811 was.
That's what I meant, 1811.
Yeah, 1811 was Krakatoa, and in Europe that was referred to as the year without a summer. But that was basically a blip superimposed upon the Little Ice Age that lasted a couple of years, and once the volcanic dust settled out, then the temperature kind of went back to what was actually normal for that period of time. But I could show you a couple of graphs here. I have here like the latest satellite determinations of the actual amount of sea ice that has occurred. There's a lot of things I wish I could show you here. Yeah, there are glaciers that are growing. There are. The general trend of glaciers for 150 years has been, they've been receding. And I can show you, let me just show you this. Take a look at these images that I've put together here. Could we dim the lights again? Okay. This would have been around the late 17, early 1800s. This is in Switzerland, and this shows a valley in Switzerland during the peak of the Little Ice Age. And here would have been the same valley in the early 1980s. And essentially you can see that the glacier that filled this valley is gone. The red arrows point to where the glacier once was, and it's basically gone. Now, did that glacier disappear? Again, remember, human contribution of CO2 began pretty much in any scale or level that where it could have discernible climate influences post-World War II. When did most of this glacier recede? Well, between 1850 and 1950. What we can see here, this is in Norway, and actually what you're looking at here is what's called a moraine. A moraine is essentially when a glacier grows, it's like a bulldozer. It pushes material in front of it. So if the glacier grows, it pushes the material out. If the glacier shrinks, it recedes back, but the material that it piled up gets left. Pretty simple process. Here's your little Ice Age moraine, and this was the glacier in about early 1980s, I think, is when this photograph was taken. So this recession, which is actually a couple of miles from here to here, took place, most of it between 1850 and 1950, before any significant human contribution to climate warming. These are some of the longest term temperature graphs where we actually have a record of temperature change going back to the 1700s. And if you look at these, what you're going to see is like right here you have a warming. This is coming out of the Little Ice Age. These are all in England. But what's interesting though, when you look at the trends of these things, you don't see anything significantly showing that the recent period of time is unprecedentedly warmer than what came before. Little Ice Age was when the Thames River was freezing over, which it doesn't do anymore. You had huge glaciers growing out of mountain valleys. In some cases, entire villages that had been there for hundreds and hundreds of years had to be abandoned because they were swallowed up to the ice. And we'll look at here, like this is Grindelwald Glacier, and you can see it's down just about ready to encroach on this village. Obviously, when this picture was drawn, there were no cameras, so what we have is basically an artist's impression of this glacier. And now we'll go to 1966, and if you look, the glacier is up there. Here's the village right here. Where this green forest is growing, it's growing on the moraine that was left behind. Most of that recession, if not all of that recession, between here and up here where the glaciers is now, took place before the Second World War, before global warming. Here you can see the glaciers coming down. This is a different glacier. Here you see the village. The glacier is moving down out of the mountains. There's another big glacier mass moving onto the valley floor here. And then we'll see in 1966 where the glacier was, the forests are growing on top of the moraine because the glacier has receded. There's another version of the same glacier. You can see there again, it's about to swallow up the village. This would have been about 1850. 1966, the glacier is way up there. And the village was saved. It didn't have to be abandoned. But again, the vast majority of that glacier recession went on from 1850 to 1950. And only around the late 40s and early 50s was anthropogenic CO2 ever considered theoretically enough to cause any global warming. So now here's what I think is very disingenuous about the whole discussion of global warming, is that what they're doing is saying, look at what the glaciers have done in the last 20 years, 30 years. Well, what they've been doing in the last 20 or 30 years is exactly what they were doing in the 120 years before that. But now what we're doing is we're saying that we're not going to talk about what kind of processes or things were causing the glaciers to recede before, because obviously they were natural. Whereas post-World War II, post-60s, 70s, and so on, now we can blame it on human warming. And we won't discuss the other possibility that there were natural variables working to cause the recession of these glaciers worldwide.
Randall, when is the next ice age, according to this pattern?
Well, let me put it that if we look in the last 400,000 years, and we look at glacial ages and interglacial ages, and we measure the span of time now of how long interglacial ages lasted, there have been probably close to a dozen, if you saw the graph that I first showed you, a dozen alternations between glacial and interglacial. The longest period of interglacial warmth that the planet has enjoyed in the last 400,000 years, the longest, actually it's several thousand years longer than any of the others, is the one we're in now. So you can draw your own conclusions from that. That's why when the climate was cooling somewhat between the 60s and 70s, which it did, and these discoveries were first being made about the tempo of glacial and interglacial ages. The concern back then was the next ice age, not global warming. Yes, back there.
If you've gone all the way back to 600 million years to determine the snowball Earth,
Yeah, that's controversial. Well, he asked me if I'd gone back 600 million years to the snowball Earth, when there's some theories out there that for a period of time the entire planet was glaciated. Yeah, I don't think it's...
you look all over the Earth and you find these drop stones.
Yeah, there has been a substantial case made for that, and it's been challenged. I haven't followed that controversy to be able to stand up here and expound on it with full knowledge of where it's at now. When I first heard that, 5, 6, 7 years ago, it was a pretty electrifying idea. It's difficult to explain, though, how you could get us into it, and once getting into it, how the heck we'd ever get out of it. That's one of the big problems. But that's an aside that probably I won't get into today, but maybe I'll research it and next time I'll have an opinion on it. Okay, afterwards you can tell me the name of it. I'll show you this real quick. This to show you that the tempo, that it was geographically widespread. This is in New Zealand, and what we see here is showing the extent of the glaciers in 1872. And again, this is not a photograph, it's a painting, but it'll still give you the sense of where the glaciers were. If you see that rock right there is about to get swallowed up by the glacier, and we're looking at about a kilometer across there, but now let's jump forward to 1905, and you can see the glaciers already receded several thousand feet up the valley. That rock is now exposed, and these hummocks, which is part of the moraine probably, or scoured bedrock, is now exposed where it was not visible here. Now notice that was between 1872 and 1905. You can't blame that on anthropogenic CO2 enhancement. Okay, and then we go to 1940, when the very first really introduction of human CO2 began to go into the atmosphere, but nobody claims that in 1940 it was enough to affect the global climate. But you can see here now the glaciers receded considerably up valley. At the mouth of it here, where it was moraine, is now in front of the moraine is a lake. Here's a graph showing the recession of the Franz Josef Glacier. And if you look at these lines, you can see this, it was up to here in 1865, and if you follow the lines from 1907 to 1930 to 1950 is about the time, between 1950 and 1965 is about the time that anthropogenic influences would have kicked in, but you can see that the great bulk of the glacier has already receded by that time, purely as a result of natural processes. So I think it's important, in fact this graph is interesting because what it does is it shows, you can see right around here, around 1950, when when our hydrocarbon consumption began to take off. But here is the graph of glacier recession, and basically you can see that glacier recession started back here in the early 1800s and was well underway by the time anybody would conclude that there was enough CO2 to influence the climate, is this dashed line right here. And what you can see is that what's been going on, and this is the thing I'm trying to convey to you, is that it's been an ongoing process. Now, are we going to say that before this dashed line, it's all natural, and after this dashed line, it's only humans? That doesn't make sense, but that's exactly what they do. Combination of? Well, can you show me, has the steepness of the line changed? It hasn't, has it? No, it's pretty much continuous.
Can you say something about the ozone?
Oh, well, that's a different question. That's the chlorofluorocarbons. That, to me, is a legitimate issue. Yes. It's yes.
Will the carbon taxes do anything to help us?
Well, it'll probably destroy our economy and make a lot of people like Al Gore rich. But other than that, no, it won't do anything. Won't do anything. Cap and trade won't do anything, except to create a whole artificial, new industry of. that'll be the equivalent of subprime mortgage derivative industry that grew up with the artificial credit expansion that occurred in the last decade. It's going to be an new artificial industry. You'll be able to sell, one company will be able to have,
So it won't slow.
I would say no, but don't take my word for it. I don't want anybody to take my word for it. What I'd much rather do is present the actual science that's out there. The one thing I will say unequivocally is that contrary to what mainstream media and Al Gore have been telling you, the debate is not over and there is definitely not a consensus. And the reason I know that is because I've been studying the damn climate for almost 30 years. So I'll say this, when the IPCC, the Intergovernmental Panel on Climate Change, was first formed in the late 80s, with the mandate to study climate, by that time it was well known that climate had changed catastrophically in the past. Nobody had a clue as to why it had happened. When the IPCC was formed to study climate, I thought, great, this is what we need. We need scientists from all over the world studying this problem because it's a significant problem. Okay, got to be addressed. But within several years, when they first came out with their first summary for policymakers, which I think was in 1992, and I perused that, I began to get suspicious. By 1996, I was convinced that it was agenda-driven, and that what the plan was to focus exclusively on the human influence, to the exclusion of all natural variables. And everything that I've seen since then has convinced me that that's an accurate assessment of what's going on. Meanwhile, all of the evidence that has accumulated has suggested that the natural variables are profoundly more significant than the human contribution so far. If you doubt that, I would please invite you to attend some more of my talks that I'm going to give. Have me back and we can get into this in much more detail. In fact, on the next Sunday, I'm doing a presentation at iDrum. I think it's a art center, community art center or something. I don't know if y'all want to make it down there. Pardon? You'll go on Sacred Geometry Atlanta and they'll have an announcement about it with an address and all of that. And I'll be going and giving about a 2.5-hour presentation on global change. A lot of it that you've seen, but most of it will be stuff that we didn't cover today. Thank you.